Paraformance tool. And if I understand correctly, this is a tool for automatic parallelization. Correct me if I'm wrong. So it's about identifying parallel regions in your otherwise sequential written code, and then providing the tool to transform it into computation code.
Thank you very much. So I don't know if you've noticed in the program that I appear to have gained a new surname. So I can't guarantee that my talk is actually going to finish, which is probably why the room is cleared out a little bit. So I'm just going to go over just a few slides, just to give you some idea of what we're up to, and then I'm going to give you a live demonstration of our tool. But I wanted to kind of start off with just a story about a Scottish startup story. So at St Andrews, we're working quite hard to spin out a company from university, and we've been quite successful with gaining some money to do this. Firstly, about 600k from the Scottish Government. This is focused just on commercialisation of the technology, but also on the back of a number of EU projects, over about £7 million worth of EU funding, I think, in total. And the idea is to spin out sometime early next year, so in April, to actually form a real company, become a real person, live in the real world, make money for a living. And at the moment we have a team of 4 developers full-time, so I can't take all the credit for this that I'm showing today. And we're looking for trials, so if any of you like what you see today, please get in touch with me, and I'll be delighted to give you a free version of the tool for you to try. So just to start off, we all know the story of multicore, otherwise we wouldn't be here. I just thought this was a nice, interesting piece of technology that I found on Google about a week or so ago. It's called a kilo core, and it's a single device with 1,000 cores built into it. Now it's a prototype device. I think it's still under research and R&D work at the University of California. It copes with 1.7 trillion instructions per second. Each processor is also independently clocked, so each processor can shut itself down to save energy. So about 1,000 processors executing 115 billion instructions, but only using just over half a watt. So that's a single AA battery powering 1,000 cores. So I think this is really the important angle of multi-core. It's not just performance, it's energy. Having a multi-core device saves you energy. And this is why these systems exist everywhere in the world today. Our lives all depend on them. Mobile phones, medical imaging, driverless cars. Okay, they're not on the streets at the moment, but they will be very soon. Artificial intelligence, simulations, all of this depends on multi-core software, or else it wouldn't work. Mobile phones depend on multi-core software, basically, so you get extended battery life and more performance. And self-driving cars, I think the Tesla ones that are already in the market use some kind of multi-core technology into them already. So this is kind of key, so they can process all of the information from their sensors fast enough to make the car work. So none of this would exist without multi-core. Of course, there's a downside, and that multi-core software is really, really hard. I think everybody can agree on that point. It's really difficult. Most software developers can't really handle multi-core software, so they either just avoid it, or they spend months and months hacking together some kind of multi-threaded solution that kind of only half works, and so on. And this kind of attitude is really what exists in the real world. So this is Chuck Norris. Everybody knows who Chuck Norris is. Needs no introductions, right? So Chuck Norris can write a multi-threaded application in a single thread. But this is really the kind of mindset a lot of people have in industry. A lot of developers think they can just throw threads at something and it will be multi-core. And that's it. Don't need to do anything else. So what we've been working on is a technology called Paraformance. And this is a tool set that basically tries to address some of these issues. So the idea is that it allows developers with minimal effort to write parallel code. It provides some kind of automated guidance, programming the loop suggestions, and ways to get their code from sequential to parallel. I'll demonstrate that to you in a short while. It increases their productivity, so rather than them spending months of their development time writing parallel code, they can actually get on doing more kind of productive things, getting their applications right, getting it to their customers faster. So this saves them money and it saves them time. It's geared not just at expert programmers, but also non-specialist programmers. So kind of your average day software developer who might not know how to write parallel code, but they really want to do that. It increases portability, maintainability of code, and it also increases the robustness and resilience. And I'll show you how our tool kind of handles these types of things. And we're also kind of trying to bake things like performance, energy estimations into the tool, so that you're not just driving your software blind. You've got some guidance on where you're going with it, and what kind of goal you want to achieve. And the technology is built on a number of different pieces of technology that have come out of research. One is parallel patterns. I'm sure everybody has come across these. Just to give you a very quick recap, these are basically kind of like high-order functions in functional programming. So things like your task farm, your parallel pipelines, reduce. These are kind of common operations, parallel operations that occur very frequently when people write parallel code. So for example, a task farm, the most common one is a data parallel operation where you've got a unit of work, you've got some data coming in, and you replicate that work over your number of cores or threads. So you get your parallelism that way, and you can send data to each worker and you can operate in parallel. Pipeline is a slightly different type of thing. It's more where you have, say, you have a composition of functions, and each function can process a piece of data independently, but they kind of change. So, for example, here S2 takes the result of S1 and so on, this good stuff. So it's like a conveyor belt of work. So you get the parallelism here where each box, each stage can operate in parallel. So there are different types of parallelism, and these things can be nested, so you can have farms inside pipelines and so on. So it can get very complicated very quickly. These have been around for a long time. They're quite similar if you're more familiar with Haskell or Erlang. For example, the Haskell strategies are kind of like patterns a little bit. So ParMap is a pattern. Or in Erlang, there's a parallel pattern library we developed at St Andrews called Skell, and that also allows you to write parallel patterns. And what we're trying to do is to bring this functional programming knowledge to the imperative world. We also build our tool on another piece of technology called refactoring. So this is basically how changing how a program works without changing what it does. So it's a process of software engineering where you modify and change your code based on requirements change to make it more portable, maintainable, etc. And refactoring, it's all about transforming the code, but also checking that the transformation can go ahead. So it's about the transformation, but also some conditions that are associated with the transformation to make sure that it makes sense to do that. So for example, the transformation might be changing all the points in your code that's required, but conditions would be, does it preserve the semantics? Do you need to change the module, the file, and so on? So the conditions are really where all the magic happens in these tools. And why would you refactor? Well, people manually refactor their code all the time. So for example, they might want to extend or reuse their code, they want to extract functions, make them more general. Often you want to correct some design decision that you've made earlier. So for example, renaming your variables, your functions, rearranging your argument orders, changing where your functions are defined and so on. Also to counteract decay, to stop your code bit rotting, you can restructure your modules and so on. And a lot of this work has been based on functional refactoring work that we've done. My PhD was in developing Hair, the Haskell refactor. I don't know if you can remember that, about 10 years ago. And also the Wrangler work by Simon Thompson at Kent. A lot of these functional tools have kind of come together, and we've really borrowed on a lot of the ideas there to build what we see today. So how does our technology work? Well, this is the basic flow of it, if you're a kind of a developer. You start up here in the top left-hand corner. You've got some legacy code, sequential code that you want to parallelize. So you first run it through our first feature, which is called discovery. And this tells you all the parts of the code that you can parallelize. So it locates the different parts of the code that are parallelizable, that it thinks makes sense to parallelize. Once you've found those bits, you can refactor it, so the tool will refactor the code to make it parallel. But always keeping in mind safety, so always making sure that the code is safe to run in parallel. And this, what I mean by that is things like race conditions, and deadlocks, and all this kind of horrible mess you get with parallelism are eliminated. So the tool does this in a number of ways, and it can also repair them. So another use of refactoring here is that it can repair these errors that occur to make the code safe when you're running parallel. And then you can deploy it on your customer's platform. And we have a real product that exists. It works across platform. We've got Windows, Mac OS, Linux. We have a Visual Studio and an Eclipse version. And at the moment we're targeting C++ because we think that's the easiest market to target initially. And what I'll do is I'll jump straight into the demo. So I know you're all dying to see it. Can I just check first, is that readable at the back? Can you read that okay? Yeah, that's good. So what I've done is I've just set up a simple demo just to kind of show you the main features of the tool, so you can kind of, I'll walk through them. This is Eclipse. You've probably all seen Eclipse. The tool is integrated into these IDEs so you don't actually have to use a standalone tool. It just fits seamlessly into kind of a normal programmer's day-to-day development activities. This is your code view, and on the left here you've got your projects that you've got set up and so on. And at the top here, where's the mouse gone? You've got a menu here, Paraformance. So this is our tool menu, and you've got various options there. I'll explain what these mean in a second. So this code, if I just run it, so this is a sequential piece of code. There's no parallelism in it at all. It takes about 10 seconds to run, I hope. Good. I thought it might have been undefined there for a second. So it takes just under 10 seconds to run, and if I just look at the results, actually it's funny coincidences. We've got, oops. It's the same factor as it's the one before, it's pure coincidence. But this is a simple just C++ program that just generates this little factor image here. But you can easily imagine this is a piece of code that does some simulation, does some numerical analysis, or whatever you want it to do. It doesn't really matter. So the first step is here. Imagine I'm a developer working for a software house. This is day one of my job. I'm told to parallelize this application. So what do I do? Well, the first thing is I need to work out where I'm going to parallelize the code. So what I can do, go to my menu, I can choose this option, parallelism discovery. See that there? And this whirls away for a few seconds. What it's doing some combination of static analysis and profiling on the code to work out where the best places it thinks you should parallelize. So you're not just looking at all the kind of loops that don't do anything. And it comes back, I've got a little here. It's got this application has one place where it thinks the parallelism should go. So here you can see it's highlighted. I've got a little kind of reporting box at the bottom. It also tells me, if I just hover my mouse over here, you can see that, I'm not sure, but it basically tells me that the runtime is 99%. So this is obviously a massively dominating part of the code. It's really the bit that's doing all the work. And what I can do now is parallelize it. So I just simply select my little counter there. And I go to my menu. I've got some options. So our tool is not focused on one particular back-end, parallel back-end. C++ has many different parallel libraries. One is called TBB. I don't know if you've come across that. It's Intel's thread building blocks. It's just a parallel pattern library, basically. Another one is OpenMP. That's a very common one that a lot of people use. But today I'll just show you the TBB stuff because it's nice and simple to get you the idea. And I can just choose one of these, so I'm going to choose a farm. I'll just make this a bit bigger so you can see it. So what's happened here is the tool said before you can continue parallelizing this code, there are some potential errors. There's some potential parallelism thread violations, if you like. And the first one says it's a probable race condition at variable k. And then if I move down to this one, it's probably a bit small at the back, so I'll just read it out for you. It says, line 58, in this loop there's a dependency, and you might try avoid it by doing the following, and it just tells me to remove the update on k with some offset code that it's calculated for me. So it's detected that there's an error in the code. Now what I can do is I can ignore it, if I wanted to, or I can tell the tool to fix it. So what I'm going to do is just ignore it. Let's just say, well, I know what I'm doing. I'm better than any tool. It can tell me what to do. I know this code works.
Sorry, just a question. It says it's an error in the code? I mean, the original code
it's a thread. So it's not an error. It's a thread violation. So it's a race condition.
Okay.
So if you parallelize this code, it's telling you you will get a race condition.
But
it's probable.
What did you try to parallelize, the outer loop or both?
The outer loop. The outer
Only the outer loop.
Just in this example, I selected the outer loop, which contains an inner loop. Yeah. I could parallelize both if I wanted to. And it's warning me again, are you sure you want to continue? Yes, I want to continue because I'm stupid. Okay, so I get this piece of code. This for loop is gone. You can see it's changed here to this parallel 4. There's some stuff there. I'll just scroll up. And it's also put this class in here as various stuff. So if I run this now, so it's gone faster, just over 2.5 seconds. So it's gone from about 9.5 seconds to 2.5 seconds, which is pretty good. And this is just a 2-core laptop with hyperthreading. So that, I need to close it and then reopen it. And you can see it's broken. The image, that's clearly not a fractal, right?
I don't know.
Well, it might be, yeah.
It's a different fraction.
It's a different. It's not the one that I expected. Yeah. So what I can do is go back. So undo, and I get my original code back. Benefits also of this approach is you can always maintain your sequential version of your code. That's usually always easier for people. If bugs like this crop up, much easier to debug a version you know is not non-deterministic. So I'm just going to select it again and reparallelize it. This time I'll show you the lambda version. It's just slightly different. So I'm going to click the box. Click this box, apply suggestions. In fact, I'll preview it. I didn't show you that last time. I'll preview it. So what we've got here is on the left-hand side, that's the original code. And on the right-hand side, this is what our tool is going to do to your code. You can see here that what it's done is remove this line 64, which was causing all the problems, because what I'm doing is updating a variable. So all the threads are racing to update this variable. It's completely gone here. And it's changed this indexing, so it's not indexing the array with k anymore. But what it's doing is it's inlining the calculation to calculate the offset to get to that array index. And it's doing that kind of without using any dependencies or previous iterations of the loop. Okay. And the tool calculated that automatically, that bit of code. So the programmer hasn't had to do anything. And you can imagine if you've got nested loops and so on, multiple variables, etc. This can get quite complex very quickly. So I'll click OK. And I get the parallel version again. This time I use the lambda version of C++, which is this horrible syntax here. It basically does the same as the farm. I just wanted to show you a difference. run it. Hopefully it's going to take about the same amount of time. Yeah, so just over 2.5 seconds, and if I open the image, this time I get a nice fractal image. So we've designed the tool to be as general as possible, and we've applied it to lots of different types of applications, so it doesn't just work on one very specific types of code, trying to make it as general for people to use. So for things like machine learning, linear programming, image processing, all this kind of different types of applications. We've had one quite nice case study, so we're trialing the tool with companies, real companies. One nice kind of case study we've got, and there's a nice document on the website about this that I'm allowed to tell you about, is that one company had a weather simulation, and it was something like 2.5 million lines of code, 300 files. There was a guy working on this for months, the guy who was in charge of this, and we ran it through, well, he gave it to me and he said, you know, there's over 1,200 potential sources of powers in this that I think, all the loops, etc. that exist in this code. I don't really know where to start with it. I've just tried randomly going through them and parallelizing it, not really getting very far. So we ran it through the tool, and it narrowed those 1,200 sites down to 27 real parallelism sites. And then within those, we parallelized the ones that came up in order, because the tool orders from the best to the worst, and parallelized it. So this is months of his efforts in about 5 minutes, reduced to about 5 minutes using our tool, which is quite a significant effort. And the performance was very good. I think we got good speed-ups. I'm not allowed to tell you the speed-ups, and I think that's some company secret of theirs, but I'm allowed to tell you the development time.
Orders of magnitude.
Sorry? Orders of magnitude. Yeah, speed-ups, orders of magnitude over their manual version.
Does that mean that's a system that has almost 10,000 lines per file?
Yes, it was huge. It's enormous. Yeah.
Right. C++.
C++.
I'm not talking about the files, I'm talking about the author. Sorry, yeah. Shouldn't.
This is the real world, Fritz.
I think there's actually a combination of C and Java.
So did Intel Advisor find those same 27? How does that compare to Intel Advisor, for
The
example?
Intel Advisor basically doesn't do anything. That's what they told us. It doesn't help them in any way. It's too low level. So I understand that the Intel Advisor was written by the compiler engineers at Intel to help them write a compiler. So it basically tells you how to design a chip. It doesn't tell you how to write software. So it's completely the wrong kind of tool for this, for most people. It just gives you too much low-level information. It doesn't help you. It takes you longer to work out what's told you than it does just to do it manually a lot of the time. So, yeah.
So what about the places that the programmer already tried to parallelize? What do you do about those?
Well,
Did you revert them back and to them convert them?
yeah, so the idea, we haven't quite got that far with the tool, but the idea is it could undo kind of previous parallelization efforts.
Okay.
So it could find them, so you could say, well, I've tried to parallelize, it doesn't work, and you can just remove it, put it back to a sequential version, or it could repair it, maybe, if it could be repaired. And you could repair it and say, okay, it's not getting speed up because of this reason, we'll fix it for you.
Okay.
That could be something we could quite easily build in, I think.
Also, it's time for questions.
Not quite, but I'm happy to take them as we go. So.
I have a question. So the example you showed, that was an instance of what we would probably call map parallelism.
Yeah, data parallelism.
Yeah, so but completely embarrassing parallelism, the data parallelism. What other patterns can you recognize? Can you recognize reductions? What about things that have already been in a position of a map and reduce? What about a scan?
Well, at the moment we're looking at parallel force maps, if you like, pipelines. For those two.
Pipeline. Is that what?
Pipeline is like, so what I showed you on the slide with the...
Yeah, but I don't understand how this... I mean, I know it's a new pipeline, but I don't get some...
Well, if you've got, for example, you've got a function call, and then the result of that's passed into another function,
Okay.
and so on. You can sometimes parallelize these if you've got
Yeah.
a stream of data going through them, this kind of thing. Yeah, at the moment we're focusing really on data-intensive code because it's the easiest way to get our product out there. It's the easiest thing to target. But there's nothing to stop us looking at much more complex types of control parallelism or task parallelism and all this kind of thing, with reductions. Things like that.
In my experience, most scientific software, which is probably your main audience, has really boring parallelism. Really, it's mostly math. It's just convoluted and hidden away. Like you showed in your example. I mean, that could have been a parallel loop, but it just wasn't written like it.
Yeah, but our target's not just scientific. It's general. So we're targeting software houses, enterprises, people who write C++ code. So scientific people, yeah, definitely part of that, but not necessarily.
But in general, I mean, for general programming, especially ones that call various libraries or
Yes.
different things, do you have a problem with inferring whether there's an effect on how do you do server dependencies then?
Well, so we can do it. So the tool can do it in two ways. So firstly, it can know obviously about the libraries that exist, like the standard, the STL libraries, the C++ libraries that come out of the box. We know about those, and we know about the assumptions we can make on what the things you call within those libraries. So if you call C out, it will tell you you're calling C out, you're being stupid. If it's a user-defined library and you don't have access to it, obviously the tool can't. It doesn't know anything about it, and it can't. So in that case, we can rely on the programmer telling us, can you give us some information about this library you're calling? By the way, we don't think it's thread safe, but it might be. And that's kind of the best thing we can do, without going into kind of analysing memory collisions and all this kind of stuff. So, yeah.
Maybe we should continue with the
Sorry.
presentation. Keep the
I'm ready for this. Show me
I mean,
Really
you don't need
finished.
enough to
I think I've only got one or two slides and I'm done. Yeah, so just to kind of conclude, so I hope Paraformance saves companies lots of time and money, because it gets their products faster to market. It also de-risks for multi-core. So a lot of reasons, a lot of companies don't want to write parallel code is because it's too risky. It takes them too much time to do it. They're not clear what they'll get out of it. But if they have a tool that just lets them do it very quickly, they can get a product that's competing much better in the marketplace. It's much faster, or it uses less energy, or whatever. It's really good for companies. It also requires them to hire less specialized software teams. I think only about 2% of C++ developers are experts in parallelism, something like that we found out. There's a huge demand for these people, and hiring them is really hard for companies. So it increases overall team productivity and also makes the software more reliable. The bug that I showed was quite an obvious one. If you imagine you've got an application that doesn't produce an image that breaks when you run it, so these things can be quite hard to find. And sometimes you won't find the bug until it's ran for a long time, and then the bug will pop up. These kinds of things are very expensive to fix. So if you want to try it out, please contact me. That's my email address. I also have a website. So yeah, if you've got any code, if you want to send it to me, please do so. We can give you a free evaluation of the product. Happy to do that. And it's in the Eclipse and Visual Studio Marketplace. So if you don't want to email me, you can just download it. And then I think you do have to email me to get a license, and I'll send you a license. Yeah, so thank you.
And now is the time for questions. So in the example that you demoed for us, then there was a race condition and you were able to find it automatically and fix it automatically.
Yeah.
In your weather forecasting
Yeah.
study, you had 27 places where you introduced parallels.
Yeah.
So was it the same story that you just automatically
Yes.
found them and fixed them, or
Yes,
is
it
it a
was.
little more
So
tricky than that?
There were some cases where the tool couldn't quite fix them, and that was just because we hadn't built the test cases into the tool. There were some other cases where it found the same errors that the developer had been working on. And there were some cases where it found bugs that they didn't even know were there. So it did manage to fix some of the additional ones. It was quite interesting. And not always just race conditions, but things like array collisions and all this kind of more complex and just simple variable updates that are much harder to see.
What language was the tool written in?
So so the engine is written in C++. The plugins are written in C# and Java. Yeah.
Have you other questions?
Now? Have you tried your tool on Spec 2006 or Spec 2000 so far?
On the benchmarks?
Yes.
Yeah, we're currently trying to go through all the benchmarks. And so we first looked at the Parsec one, which is a kind of obvious thing to start with. And the spec ones, we've started to do a couple of the examples. That's quite nice. Because it looks quite real code, but it's good to run the tool a lot more complicated looking code. So test it out.
And also, I would like to, if you can say a couple of words, not necessarily, you can talk, I'm sure, for hours about this, but how does this work compare with other research automatic parallelism compilers?
Oh,
mostly from the Fortran 77, like Swift, Polaris?
well, controversially, I'd say these automatic compilers just don't work. That's what I'll say. So a lot of work done on automatic parallelization in the 80s and 90s. They work very well if you've got very specific types of code, like maps, very trivial things. But if you've got more complex stuff, they just can't handle it. I think what the advantage we've got is because it's all transparent program in the loop. We can rely on the programmer being a little bit smart, and they can direct the tool. So if they think, I know this bit can be parallelized, they can always direct the tool. But you can't do that with a compiler. You always have to rely on the compiler being able to solve everything for you. Another problem with compilers is that often you don't see the result of it. This is a big problem for a lot of companies, because they like to see what the tool is doing to their masterpiece that they're releasing into the world. And if you're just putting a black box compiler on it, you have no idea what it's doing. And then you deploy it on a customer platform and it breaks, you have no idea how to fix it. But the advantage of this is you see every single step. And if it does break, well, they know what the code is produced, so they can then decode it.
Well, there are the source-to-source compilers, which is the research ones. Swift, Polaris, they are all source-to-source.
Oh, right, yeah, they are.
Fortran with OpenMP annotations.
Right. But they don't fix the errors. They don't fix the errors and they don't target multiple.
No, they do in the sense that they fix induction variables, substitution, right, privatization to some degree. And for example, in this work, do you have anything that would suggest, like, some loops are not statically parallelizable because they depend on the data sets, or on assumption of whether some arrays that are using an indirect array accesses are monotonic or not, or some such.
Yes.
For sparse. Do you handle such cases?
We're starting to handle things like the indirect array issue that you were mentioning. We started to build that into the safety checking so it can detect that. A lot of it also depends on the thing that you're targeting. So what, for example, OpenMP or TDB itself can handle. So we've built a lot of this stuff. Like I showed you the TDB, it's quite simple with patterns. OpenMP can do a lot more complex stuff, so it will open up a lot more doors, if you like, once we start to target that problem. But these types of issues, yes, I think in time we'll be able to target.
Because that would be a really cool thing, because now we can actually put the pressure on the user to say, we have discovered if this invariant holds, by the way,
Right, yeah.
you can parallelize this,
Yes.
so then the user
Yes.
know whether it's
Right.
or not, and the compiler.
Exactly, yeah.
Other questions?